Welcome back to week 11 of inverse methods in heat transfer. In this video, we'll be looking at an important modern technique called physics-informed neural networks. Pioneering work in physics-informed neural networks has been primarily done by the Crunch group in Brown, headed by Professor George Karniadakis. But before this, there was actually a very similar, in my opinion, paper by Lagares et al. This is sometime in the 1990s. I think the paper that I am going to show is Lagares 1997. So what I would like to do is to think of physics-informed neural networks, also called now called PINs, in two steps. First is PINs for forward problems, and then PINs for inverse problems. In my opinion, it's in the solution for inverse problems that PINs really shine. In forward problems, you will see that they offer a very nice alternative to traditional techniques, the CFD technique that I introduced you to in the last week. But really speaking, their major power comes in inverse problems where you do not need any large-scale simulations, as I had shown you for the case of surrogate models in the last week. So this is a very, very interesting idea. Like I said, first introduced by Lagares et al. I'll show you the paper. But let me first briefly introduce you to the idea. Okay, so the idea is this. Suppose you have any ODE or a PDE. Okay, so I'll take an example ODE or a PDE. So let's take some ordinary differential equation. Let's say we have the equation d square t dx square equal to some source term. Let's say some volumetric heat generation. In this case, let me give you an example. Let's say volumetric heat generation looks like x square plus 3x plus 1. Okay. So the way you would solve it using CFD would be you would make a mesh and you will take these points in the mesh, some points, some random points. So let's say in this case, delta x is, let's say this goes from x equal to 0 to x equal to 1. And this is x equal to 0.2, 0.4, and 0.7. Let me make it uniform and add one more point here. Okay, so 0.2, 0.4, 0.6, 0.8, and 1. So then you say something of the sort that this is I equal to 1, 2, 3. These are grid points, 5, 6. Then you will have a relation such that ti plus 1 minus 2ti plus ti minus 1 that comes from here divided by delta x square, which is 0.2 square, equal to xi plus 3xi plus 1. So this, if you see, the right-hand side is known. The left-hand side basically becomes a matrix. And you will have something like T1, T2 up till T6 equal to some RHS. So you'll have some matrices which will look like 1, minus 2, 1, 1, minus 2, 1, and it will be a tridiagonal matrix. In case this looks too fast to you, please do take a look at a basic numerical methods course. My point here is traditional CFD solves for these points separately. So each of these solutions is a separate solution and you solve for that. Now here is the PIN idea. The PIN idea is this. I know that T, the solution, T is a function. Particularly, T here in this ODE is a function of X. Okay. Now, the way we solved CFD was not to assume that it's a function of X, at least not explicitly. There are implicit assumptions here in terms of piecewise linear, piecewise quadratic, etc. So you take these 6 as separate unknowns. Okay. You have to, of course, give boundary conditions, which I am skipping briefly for now. I'll come back to the boundary conditions issue very, very shortly. But for now, let's just ignore the boundary conditions of the problem. But if we just look at these separate solutions, you actually get separate solutions for CFD at these 6 points. Now, there is a different method Once I know that t is a function, t of x, I can say approximate t with a neural network. What does that mean? It means here is a diagram. I take x, this is the input. There is some neural network here. For example, there could be one hidden layer, multiple hidden layers. We have already seen these examples. And the output here is t of x. Now notice, even though, as I have said it multiple times, even though I draw this as a diagram, every diagram, you would have seen this in the exercise also, is equivalent to an analytical function. For example, if I take x, just have one neuron here, which is sigmoid, and this is W1, and I have a linear output here, y, or let's call this t, just to be consistent, t hat, and this is W2, then this will say that t hat equal to sigmoid of W1x. Now this layer will multiply this, multiplied by W2. So this then is a function. Okay. So t hat of x is also a function. This also is a function, except it's a complicated function. Now, how does that help us? Once I know that it's a function, the way I do it is as follows. You assume some architecture. Architecture means number of neurons, number of layers, etc. Assume some architecture for t of x. So it could be like something of this sort. X, t of x, okay, etc. Okay. Okay, here there shouldn't be any layers, but anyway. So then use or find d square t dx square. How do I find out d square t dx square? Once I know this can be done through backprop, or what is known as automatic differentiation, which we saw in the last week. So for a given t of x, you can find out what d square t dx square is, and then solve let me show this a little bit better. Then effectively solve d square t dx square equal to some RHS, let's call this f of x, by minimizing summation of d square t dx square minus f of x, all of these calculated at I over lots of points. So the way this works is as follows. The same domain, I take lots of points. Now, unlike CFD, these points have a different purpose. They don't have to be uniform. These are treated basically as data points. I'll show you the brilliance of this when it is applied to inverse problems later on, but these don't have to be uniform. You can basically treat these as data points. So let's say we have 1, 2, 3, n data points. Okay. Now, the general process is as follows. The process is make a NN approximation. What do I mean by make an NN approximation? Choose. So let's say I can choose a number of layers and neurons. So let's say for the differential equation that I have shown, I make a simple choice. So for example, I choose one hidden layer plus 5 neurons. If I make that choice, so this is what it will look like. X, then 1, 2, 3, 4, 5, and then T. Okay. Now, what's the problem here? The problem here is we don't have these weights. So W11, W12, etc. with unknown weights. Okay. So let's say our weights are also unknown. Okay. So we have a whole bunch of weights here. Let's say we have weights and biases, but let's say just weights. So let's say in this case, we have 10 unknown weights. Okay. So what do? We do the usual thing that we do with neural networks, guess for these unknown weights. This also looks simple. So we just guess for these weights. All right. So we have an initial guess. Now we need to improve. Do the forward pass. Okay. So we do the forward pass. How many times? N times. Let's say I have 100 data points. So for each X location. Okay, so if you have a domain going from 0 to 1 and you have 100 locations randomly thrown, you throw these 100 locations, do a forward pass. Now what will happen is for each Xi, I obtain a Ti. That's fine. But notice there is no ground truth. I don't know what temperature is supposed to be here. So how do I do a back pass? How do I find out a loss function here? So here is where the genius of Lagares is. So you define J as I showed earlier. You define J not on Ti but on derivative of Ti. So J here is d square T dx square minus f of xi. So the loss is what I would call the ODE loss. So we will call this JODE. Notice if you had the data there, you could have used it, but you don't have the data. But you do know, one secret in this domain. It's not as if nothing is known about what happens here. We know that at every point, the ODE is satisfied. So regardless of where you sample, even if you don't know the temperature, you do know that the temperature satisfies a certain relationship, which is d square T dx square minus f of xi is supposed to be 0. Now, instead of setting that to 0, we want now we can't satisfy that every point, but we can minimize it. So instead of doing this, you try to minimize which would be the same as trying to force it to 0 if we can do so. Okay, so what we do is we simply create a loss function, which is the sum of the individual residuals of the ODE. Okay, so this is a very simple but powerful idea. But you will say, okay, I had only TE during the forward pass. Where do I get d square T dx square from? Now notice X led to T and it's an analytical expression, which means that through backprop, just like I can find dt dw, the process that I showed you, I can find out dt dx also. And in fact, I can repeat this backprop twice and I can get d square T dx square. So when you calculate d square T dx square, this will be a function of the W's. For example, let's take the simple case here. T hat equal to W2 times sigma W1x. This will mean dt dx equal to W2 times sigmoid prime W1x multiplied by W1. Let me write it here just to be clear. So in case T equal to, let's say, W2 times sigmoid of W1x, or let me replace the sigmoid with some general function g of W1x. This means dt dx equal to W1 W2 g prime of W1x, which is, if you notice, another function of x as well as W1 and W2. Next, d square t dx square equal to W1 square W2 g prime W1x. Okay, so notice this. So when I give you a new x, I have, let's say, 100 x's. So if I give you x1, you can calculate this at x1. You also have the right-hand side, which was some x square plus 3x plus 1, let's say. So you do x1 square, calculate this. Okay, so this for a given x1, you can calculate this. Then you can write d square t dx square minus RHS of x. This will be the loss function. You can calculate that. Okay. Now you have the last step. So basically J has been calculated is sigma of your d square t dx square minus the right hand side of x square. This is just the ODE loss. The final thing is you want to find out improve W. So W becomes W minus alpha times del J del W. So you do this for all the 10 W's, then W is updated. So now run in a loop. At convergence, you obtain W. Now, once you obtain W, it means you have T of x. Why? Because T of x was simply a function of x and W, which means unlike CFD, which gave you solutions only at 6 points, this gives you T of x at every x. Unlike CFD. Okay, CFD gives you only at discrete x points. So the difference between PIN and CFD is PIN treats the problem as an optimization problem. What are you trying to optimize? You are trying to minimize this function. Whatever be the function that you are trying to solve, you are trying to minimize that function. I'll make this a little bit cleaner in the next video. CFD, on the other hand, is solving this directly as a ODE residual, ODE or PDE residual. Second is you get the full solution at every point. Here you get solution at discrete points. Finally, this mesh is not very important. Okay, we will see how that affects things shortly. Whereas here mesh is very important. Because depending on how I give the mesh, my difference equation or my difference approximation actually changes. Now, there are a few things that I have not discussed here. The things that I have not discussed at this point are how do I incorporate BCs. Second, how do I solve inverse problems? And of course, some developments in this field. Okay, so for example, I want to talk about what the general idea of Lagares was, how that was improved by Raisi and Karniadakis. And then there is some work that we did even at IIT Madras regarding this to improve upon this method. So these developments I'll discuss in the future videos. This was just a very brief introduction to the idea of physics-informed neural networks. I'll also talk about why they are called physics-informed as against something else, which it becomes obvious once we talk about inverse problems. But before I go further, I just want you to remember one very, very key point here. There is no data. Okay, unlike let's say a normal neural network where you give some ground truth, the ground truth here comes from the differential equation. So the truth that you're trying to talk about is the fact that at every point here, you can choose any point in the domain. We know that the differential equation is satisfied. That's the genius of the method, which was first introduced by Lagares. So the idea is this: every point here, you can apply this loss function without any doubt. Even though you do not know what t is, you do know what d square p dx square minus f is. So I will show you a simple example of this, without the confusion of the neural networks in the next video, and then we will proceed with what exactly Lagares did, Raisi did, and other developments in the next video. So I'll see you in the next video. Thank you.